first speaker is from the University of Minnesota and ETH, and she'll talk about the landscape law and wave localization.
Thank you. Thanks for introducing me. It's a huge pleasure to speak here again. Thank you to Schrödinger for the invitation for organizing this one and for everything we got so far. And thanks to Carlos for participation for the first half of the week. So as now I'm going to talk about the well, most of the talk about the landscape law, which is a new variation of the while, I would say, hoping to convince you more efficient for certain kind of problems, as while law seems to be very much a topic so far, and generally the subject of wave localization. First, a few introductory words, since everybody seems to be trying to be introductory. The punchline of the entire story is that sort of miraculously, a solution to one equation gives a lot of information about all eigenfunctions, and the difference is that the solution is unique. We're able to collect information on eigenfunctions, so the eigenfunctions for which there is a significant number of solutions, even if you discrete spectrum. But here, really, one solution sort of of the bed contains enormous amount of information. And as far as Schrödinger equation goes, the solution is rather surprising in the sense that it's not very physical. It's really a mathematical invention. Sort of should sit about this. The language is not a physical information really. So among other things, it gives the pattern of the exponential decay for localized eigenfunctions. It gives the actual regions where the eigenfunctions are localized. It gives very precise information on the spectrum of the energies. So first is the spatial information, second is the spectral information on the energies of localized eigenfunctions throughout the spectrum by one mechanism at the bottom and by another mechanism throughout. And so this and this are proofs. And I'm also going to be talking about things which, conjecturally we have to be true, which is the connection with the ability, which is sort of the holy grail of this entire business. I will tell you which time comes, spectral function, and functions. So the first three things are theorems, the other three things are sort of conjectures at this point, but I dare to say, just as curious and to be more interested in everything. Not proved yet. The subject is by now, as many of you know, part of this huge science collaboration for wave localization. In the top, this is actually not complete list of people who are right now with the umbrella of the collaboration. The important people are the guys. No offense. Somewhat less important people down the list. Okay, let's put it this way, junior. More junior people are down the list. And well, it has been for us. So one of the guys evaluated many functions that fits medal, and 2 days ago on Spain, another guy got the Nobel Prize. Kind of harvesting perhaps too much here. And both are actually very much, the main results in both directions. Alan's work, which was very nice, and you guys' work are very much in line with it. So first of all, I mentioned, and I promise this will be the only not a practical slide, quasi, but again, the collaboration spans anything from pure mathematics to applied mathematics to physics to experimental physics, really substantial project all the way to engineering. And in addition, just to mention to you that that's for real applications, in addition to the Fields Medal and Nobel Prize that I've already mentioned, the DOE has announced a new, slide outdated slide actually, but DOE has announced a new energy service forecast for energy highlighting of the United States. And they have originally, well, originally it was 2017, but the goal was 2035, a goal of 50% improvement in energy efficiency, which is energy saving. Well, to give you an idea, this is a slide for engineers, I understand numbers say nothing to you, but this is 10% of US power. So the idea is that if everything goes well, then the energy mean, scientific obstacles are overcome, then energy savings in the US, purely, from the scientific progress, will be about 10% of the total. Well, there is also an amount of money because I'm talking way too much to the foundation, so I always have attached money, so that would be 890 billion. At this point, we have 33% improvement. So there are main engineering goals. I won't be explaining what they are exactly, but at this point, we have 33% improvement on green gas, so 70 are remaining. And another point is the lack of accurate computational modeling, and there is 1,000 times at this point. So we are not there yet, but we are well on the way, given that 2035 is not exactly tomorrow. So these are the far end of the engineering results. The rest of the time but this is trying to give you an idea that in 3 years of the computation, we went all the way from pure math to engineering. This results with a couple of different things. Okay, so let me haven't talked about the sense yet, and possibly for some junior people and audience, relatively new. We are going to talk about the Schrödinger equation, and specifically the Schrödinger equation with the disordered potential. And the idea behind the entire collaboration subject to this point is that the technology is at the level of experimental physics, is at the level where atoms can be handled individually, and atoms can be mapped. This is actually the map of atom proton operators, billions of atoms at a time, every single one, things like this. So you can actually, to me, it means that you can transfer mathematics into physics basically without errors at an atomic level, which is sort of an amazing model. But simultaneously, it raises mathematical questions, and it really needs mathematics because, okay, you map something billions of atoms at a time, what do you do with billions? You actually need mathematics to make some predictions as to what you want to achieve. It's not a trial and error. This precision, this size of sample. I'm trying to avoid the word big data, but this is actually big. So what happens in the presence of disorder? Well, curious things happen. So you have a Schrödinger operator, you have no potential, you are solving a problem on a square, you have a class of eigenfunctions, you know what they look like. You have a smooth potential, something like this. The situation is distorted, but not so much. In the presence of disordered potential, something dramatically different happens. And in terms of mathematics, sines and cosines are actually becoming exponents, so completely different objects. And in terms of physics, the former conductor will become an insulator. So on the top is the potential, which I will be using a lot. So I'll introduce it at this point. This is our toy model. We take a square, we show random squares. We assign random values on the square. This one's will be uniform. More often I will be working with one, which is 0 and 1 random, it's 3 square model. But basically, yeah, results all of those and think about disordered things, what disordered does. Eigenfunctions. Anderson localization itself, I mean, the particular example that I showed in the previous slide is the so-called Anderson localization. In itself, it goes Nobel Prize. But I mean, the work was actually done in 1950, but there are many open problems. There are beautiful mathematical problems. rho expansion and doesn't start. Bernoulli for the one I haven't yet introduced, it's due to Protein and Koenig. But all of this is still at the bottom of the spectrum. It's not clear. There is basically no proof of delocalization. So we know when something localizes, we don't know that it doesn't. And more importantly, we don't know where is the mobility edge, because basically the deal is that they cannot be mixed. You have a localized phase and then a sharp transition and the delocalized phase. So at some energy, life changes. And the question is, what is that energy and what are the critical exponents of this energy? And in short, there is no simplification. Generally speaking, I mean, some particular models have some sense, but really no sense. So there are many open groups. One thing is difficult to talk about this. We did go a little bit sort of behind the scenes between classical and quantum already in some questions and conversations at this conference. But then I mentioned to you that, of course, the deal is that the wave is not a particle, and it has tunneling, so it can go through the holes a little bit with exponential decay. If you have a square wave, you have a particle just sitting there, the wave can actually cross, but exponentially decay. But the potential that you see on the right hand side here, and now it's finally Bernoulli potential, 0, 1, uniformly. And I'm consciously choosing and will be choosing the situation in which probability of 0 is bigger. So if you go to particle, you could also. So all the models I'm talking about, not necessarily, but I'm saying that in particular, everything I'm talking about includes the case where you could not do anything from the classical point of view. The concept of going to 0 and seeing what happens classically doesn't exist, meaning just there's no information, because classical particle would just go through, it wouldn't localize the way it localizes. And this is the logarithmic scale, so this is very severe localization. This is exponential. So basically, your vision is wrong in both directions. I mean, what we've seen with humans is not the same thing. And that's sort of exactly the punchline of the project, that this mysterious object, the landscape, the solution to H equals 1, H being Schrödinger, so H is always, well, mostly single one. I probably can't present results like this, so H is the solution to H equals 1 sort of tells you what the world looks like in the point of view of the wave. It's as though when you look at the system, you see the potential, the disorder, the composition, geometry of the domain, things like this. When the wave looks at the system, it sees something different, because again, your holes are not the holes, the wave, but simultaneously your passages. So this landscape actually allows you on sort of bubbles of the wave and see the building of the waves. And it helps you to predict the location of eigenstates, the eigenfunctions, the rate of exponential decay, the energies, things like this. And by now, again, it's a huge edifice, so there are so many theorems, many results on one head. I'll see how much I managed to present to you, but I'll try at least, something in geometry, something in energy, something in bio, and something that we don't know yet, just to give you an idea. So first of all, shooting through some first results. First thing that we have figured out is that the landscape sort of lets you predict the main regions of localization, and I will say how in 5 seconds. It turns out, and that's sort of more miraculous, that it gives you the rate of the exponential decay. So basically what happens is as follows, and that's why I'm calling it a transformation. If you conjugate the initial equations, you come up with another equation where now you have a more non-trivial matrix. So instead of Laplacian, you have this one. But more importantly, you have 1 over u in place of the original potential. And otherwise, the eigenvalues and eigenfunctions are the same. So you didn't lose any information in transforming from original equation to the landscape information. On the other hand, I claim you gain a lot because in this disordered, unclear picture of the regional potential, one value actually gives you very clear wealth, both sort of a lot of information in one value. Then, so let's see what it looks like. It's still not a simple option. I mean, this is an example of the landscape. Could be insane. It's not simple, but it has the structure of chambers. You know, it has the structure of chambers or walls between them. It's a much more precise ordered structure. You can use, so what this slide says is that, get back a little bit. You know, this is not the Laplace Differential operator effects. It looks painfully slow, but it's kind of not. If you really want to, you can see it as, you know, Laplace Differential by plus V in some, you know, word product space going one dimension up. But to be honest, we have never managed to actually prove something using this observation. I very much hope there are deep connections, in particular with things presented in this conference, but so far that's not the way we do things, because once you do the word product, you are in one more dimension and you are sort of losing localization, because in that other dimension you are never. Then the pain of you know, figuring out what's important, what's not anymore becomes sort of surpasses the advantages of actually using it for endpoints. But yet again, I think that's because we are probably not doing everything. But anyway, so theorem number one, how does the exponential scale work? You take your original equation, so I'm taking d by grad plus v more generally than just Laplacian plus v, with a bounded positive potential, that will not just shift up. Let's say on the region domain of C1 manifold, you take a level of, so you solve for L equals 1, right? L and the region, same thing, depends on whether my slide was planned from mathematics. So L and H always the same thing. So you solve for L equals 1. You in the office, you look at 1 over u instead of u, so it's a non-linear transformation, it's a non-linear object. You get something like this. This is one-dimensional picture, but again, so in three-dimensional you saw on the previous slide. You cut at the level of energy E, and then what happens is that what's below you cut. So you're asking yourself, where is the eigenfunction of energy? You have cut at E. What's below your cut is a well where the eigenfunction would be located, or you know, if there are several wells, it would be in several or one depending on resonances, but basically this gives you the location of the eigenstates, and the remainder of it gives birth to a metric, what we call an unknown metric, but sort of a natural metric on the manifold given by 1 over u, which gives an exponential decay. So basically the theorem properly formulated is that you know, the eigenfunction of full energy integrated against the exponent of this metric is finite. In other words, morally speaking, psi decay exists e to minus 1. Decay exists e to minus 1. Generally, there is no better than the 2, because generally, you know, the generality that I formulated eigenfunctions necessarily gets found. Well, actually, this generality they are boundable, but so this is the cleaner mathematical thing. Now you could say, well, this is the number one more, because I'm saying this is finite, that's all I'm saying. And keep in mind, potential is finite size, normalized size 1. Well, secondly, you know, like any theorem has its level of precision and everything. So how good is this estimate? Well, this is back the case of the potential that I started with, the irregular potential. This is an example of, you know, sort of random seed of potential and random seed of eigenfunctions. So this is logarithm of the eigenfunction, so this is the decay exponential scale. The eigenfunction is somewhere here, these are the levels of decay. We go to 10 to minus 36. And this is the non-results using it. They're not identical, but you know, they're fairly close to 10 to minus 36. So the precision is actually there. the key objects, and I'll be coming back to this again and again. One of the key reasons why this actually works is what we came to refer to as uncertainty principle. And basically, it's the fact that this transformation allows you to transform the energy, the kinetic plus potential energy of the entire system into something in terms of U. That's half of the same. But the important part is that the reduced kinetic energy, the new bit over here, is actually rather one. Basically, the entire information is absorbed and it's positive. That's the previous covalent theorems. It's almost zero, which is more important for actual shocks. So basically, everything is absorbed and the effect of potential. So morally speaking, to us, the uncertainty principle to the skull, the uncertainty principle is something that tells you that kinetic and potential energy not simultaneous revenge. This basically tells you what kinetic plus potential energy is with a certain precision to a certain extent. But this is, one of the core principles behind these results. Once you've got that, you can have a diagonalization. So what it means is that you have sort of chalked into the regions which one value has predicted for you, and then the big eigenfunction of the system is sort of with exponential precision is one of the big eigenfunctions of the small regions. So this also can be solved. I won't go into this too much, but basically it gives you the spectrum with exponential precision. And I will also mention that, so this is the result which sort of came at the beginning, and by now there are many generalizations. So there is the one magnetic Schrödinger. I put Bruno Kochi here, so for student, his one actually Stefan just sent me another one and I didn't read it yet. So do you have collaborators there? Should I, so whomever, last, I don't remember. Gives another magnetic version of the landscape. What else is fun? Many body localization actually done by physicists. To me, like with some very big space, but that was nonetheless. And this is what sort of started the work with Viktor Galitsky and Laura's John's student postdoc. Sorry, now they don't see her, but she's somewhere. There, yes, I do that. So this is a very ongoing collaboration, and my affair is another science collaboration. And the result goes the way to random matrices, and this is the results with the power of our cell and functions. So first of all, with the magnetic case, basically, I'll just tell you this, that what Bruno has is a new version of landscape for magnetic Schrödinger. The challenge for magnetic has a potential term. It has a complex term, complex value solution. So what do we do with that? So it introduces one version of the landscape and then proves for it transforming the principle, and there you can do this Egman-like results. My understanding is that Stefan and collaborators are slightly different. Again, I haven't read, so I won't say much about it. As far as the random matrix goes, so this is a slightly different game from a slightly different universe. In random matrix theory, the typical question is how localization depends on the bits of the matrix. So the point is basically that you have a matrix in which single W diagonals would be in random and the rest being zero or rapidly decaying. And the question is, the conjecture is that depending on this randomness, you have a little more localization. Whether the matrix is full or whether the matrix is Schrödinger, of course, right there. There is a randomness on the one there, at least in 1D and sometimes higher dimensions. So the conjecture is that Schrödinger and beyond all the way up to N1 have localized and otherwise not. But we're not very close to the conjecture in that direction. The similar results to the one I showed you already, however, are actually true. So in particular in the Wiltshire matrices, so these are the ones where all diagonal elements are positive. They are very common in statistical physics, and mathematics we can just say the ones where you have signs or sign elements. So you look at the matrices, and it turns out that you can actually pull off the same story. So it's not so much about Schrödinger; it's a much more general phenomenon. You can define U as A minus 1, 1. You can define a graph associated with this matrix, of course, weighted with the values assigned by the elements of the matrix. So there is a geometric universe associated with this matrix in which you basically have the same kind of decay. And again, this is the Argand style decay governed by one review. The good news, it sort of indicates the conjecture part of decay. It indicates the conjecture result from the previous slide, so it actually gives the correct powers or exponents here, the rate of decay. The bad news are this is not the proof of localization and localization because the wells can resonate. So this is sort of a precursor. But the results are nonetheless true. And well, here you can see examples just so that you believe that I'm not, cheating anywhere. So this is, these are different regimes, but basically this is the landscape. You can see here in blue. And well, the eigenfunctions are pretty faithful for the localized. So in colors are different things. I'm trying to say that the same thing holds and creativity. One more thing I should mention before, so this is really harder than just discovered a few months ago and very much conjectural. But nonetheless, it proved this probably would be major progress in the localization business. So this concerns this mobility age. The difference, the threshold between localized and delocalized. It has always been believed that mobility age has nothing to do with percolation. For a stupid reason that, again, I just showed you percolating potential, like fully percolating potential, in which there is localization. So obviously, you can't have percolate. So if you have original potential, the mobility age is here. Zero. The percolation. But if you do it with the landscape and you compare the actual mobility age to the percolation threshold of the landscape, the situation is very different. So it's most definite that it's still right under, it's not exactly measured, so there is a difference between quantum and classical percolation here. That's still subject to trying to assess it. But it's definite that there is connection between the two. And another picture in which you can see it, so this is a more standard for people in mass physics map of the world, the localized eigenfunctions, the energies, volume of the potential, the maximum of the potential. So you can see experimental data in various versions of black. They slightly differ because the results of experiments are slightly different, but the prediction of the landscape isn't big. We cannot do this threshold, but at least this one, the landscape predicts rather basically. And again, I'm not going to go into details, I can explain to you after what the two edges actually mean. But basically, it gives one side the mobility edge. Once again, this is pure black magic right now. Now, in order to assess this, in order to even speak about calculation of the landscape, you need to understand landscape as a probability object. Because what are the properties of it? Probabilistic properties. What is the law? What is the covariance? What are the correlations? All that. We have some idea of it. So this is a joint work with David and Gloria. Just finished. I don't think it's definitely not an archive yet because I haven't. Okay. But we're fairly sure about the results. So we know landscape as a probabilistic object. What I'm trying to say. From here, one should be able to study percolations. People hopefully have Hilda. And people who work with Hilda, but this is the next order of business. Okay, as far as eigenvalues go. So there are two ways to assess eigenvalues from the landscape, and I'm actually not going to speak about the first one just for the sake of time, although this is quite interesting. I'm going to speak about the one, since so many people have it. So the one was supposed to give you integrated density of state, the number of eigenvalues below the energy level. if you ask yourself what is the number of eigenvalues below it. In the world of Schrödinger equation, phase vector should be the volume of the phase space delineated by k squared plus v less or equal than e. Right, well, sort of, but there's always while law is an asymptotic result. It's a result which is true as energy goes to infinity. It's nowhere near being true near zero, and for disordered potential, that basically completely misses the point. Because for a bounded disordered potential, yes, of course it behaves like a Laplacian with high energies, but that's not the Laplacian. So this is an example, in blue you have the truths for one of the potentials I will describe it. So this is everything. It's a step function. You click up every time you need an energy. In green, you have the while law, which the while law here is the original potential V. Again, it's true asymptotically, but it's miserable at the bottom, and asymptotically it's easy for us to find a potential. And then if you switch from V to 1 over U, well, the red one is. So there is no need to advertise, it's a much greater precision. It's still true and asymptotic, but it looks like it's true in some sense, starting from the bottom of the spectrum. And from this many experiments to use in physics, to do trivial problems, so all of that, it still wasn't proved for a moment. I mean, despite the fact that physicists and engineers started using it like 2 days after they started it. Even formulating the mathematics turned out to be extremely challenging because, well, basically there is no markup for the value, which is not asymptotic. I mean, how do what do you measure your error? I mean, this is almost like this, but not exactly the same. And you don't have a floating parameter. There is no H here. And there is no H neither morally nor generally, just because, taking a limit in H would be also taking a limit in energy. So that's exactly what we're trying to do. We want to get it from for all possible energies. So what do we do? Well, two observations. So one, which I didn't tell you about, again, I sort of skipped it, but at the bottom of the spectrum actually bore us through. We could even predict the eigenvalues from just minima of 1 over U. And secondly, you have this, markup of while law, if you wish, the while law is 1 over U throughout the spectrum. But you perfectly understand that neither can be the ground truths, meaning they are not actually equal. None of them is equal to integrated density of states. So then you start, asking yourself what is known, and the general idea might be try to understand what potential makes up a good one, and then maybe to see why 1 over U is better than the original potential V. The while law, there is none of them which sort of answers this question. I mean, if the potential is expert, then yes, you are in business. There is no sort of recipe for or efficient recipe for what kind of potentials, how an improvement in the potential. And dramatically alone, very simple potentials. You take, two uncoupled harmonic oscillators x1 squared plus epsilon x2 squared, just that, while there is already infinite minimum numbers. So it's completely useless, irrelevant information. That was already somewhat helped by the so-called confinement, which was a great invention. It ultimately led to the stability of matter and other big results. And basically what they observed is that you can sort of build up from the original potential V certain maximal function, well actually maximal function is produced by Localization, but the idea is from Fetterman and Fon, so you can build another potential which does better. It does better, and again it does help on a lot of matters, but it's still completely wrong for others. So it absolutely does not address the problem that I'm trying to work with, which is the case of this disordered potential. It basically has useless as the original one of disordered potentials. but it contains a lot. I mean, it's really, like simultaneously completely useless on the surface of it, and was super useful for the blood feeding. This result is velocity, it's feeding, everything. And then on the other side, there are mission still estimates. So this is the behavior of the near zero of the spectrum of the potential. This is how the energy takes over. But the problem is that it's asymptotic decay. The value is asymptotic at infinity, so this is asymptotic at zero. Again, asymptotic and very, very different. So it's not matchable. It's not matchable in any possible way. And again, it's an asymptote. So it doesn't tell you how the structure is. So long story short, here is what actually works. So Sarah, something that I'm going to refer to as the landscape law from now on. You take your original Hamiltonian, you compute the landscape, and what you're going to do is you chop the space into the cubes of side lengths lambda to minus 1/2. That's of course a natural side lengths. And then you count the number of cubes on which the minimum of one irregular less than 5. So this is the counting function, which is purely defined by the landscape. And the landscape, you just count the minimum. And the claim is this is enough, without any estimate. So there is an estimate from above and below on the integrated density of states in terms of the counting function. It applies to absolutely every potential in the world. There are absolute restrictions to the potential here. The most general version is a bit from below. But definitely, for any potential that you can possibly imagine, if I'm putting a few examples that I like as harmonic, if U squared is another weight, or if D is one of these other potentials, then you have an honest estimate from above and below without any adjustments. So you have the landscape, you compute the counting function, you have the bound from above and below with dimensional constant. I insist on dimensional constant. There is no dependence on the eigenvalue here. It's not an asymptotic result. There is no dependence on the size of the domain. There is no dependence on the size of the potential. There is no dependence on any sort of norm of the potential. So I'm formally, when I actually was proving it, we're formulating with finite V and finite domain simply to make sure that there is definition of the spectrum and everything. But everything goes in the limits because there is no dependence on the parameters. So long story short, with this, you give birth to some sort of a non-asymptotic while law. Yet again, without dependence on lambda or size of the potential V. So it's true for infinite potentials as well as long as the limit is meaningful for infinite potentials. The only thing is it needs to be bounded from the law, because there should be a solution for the landscape. And yet again, I sort of like localization problems because that's what we're working with, but this actually has nothing to do with localization or lack of that. It's absolutely reverse. One of the outcomes in the particular case of the understood potentials is you can get now estimates and you need to tell me that you produce from one thing that you don't know, another thing that you don't know, which is the landscape counting function. Well, the truth is that again, this is one object, so it's extremely easy to compute, but it's also much easier to manipulate mathematically. It's a very nice solution to the elliptic equation. So getting rid of it and getting sort of clean estimates from above and below is actually relatively easy. So manipulating this counting function for the landscape is really much easier than manipulating the original problem. And you get all these variation interactions that physicists like the different kinds of potentials. So there is really an improvement from low estimate, which was the best known in some cases. Another example which I do want to mention to you is sort of complete opposite end of the story, but it tells you how sharp this is something that came from the Charlie Peppermint's third on that sort of principle. This is not about localization at all, but it tells you that the result is super sharp. So if you take the operator, which is Laplacian minus k over x squared, then you have a positive operator plus an negative potential. So at some point they converge, meaning that up until some k you have unbounded the whole spectrum, and then at some point you have a bounded spectrum, so a positive operator. So there is a transition at the given k. This transition could not be predicted by the standard while law at all. I mean, it just incorrectly gives infinity for all k, and that's again, I mean, it's actually bounded for up until some threshold. The refined Kepler-Mann-Cohen uncertainty principle would give you the fact that there is a constant which gives the transition without, any clarity what's the constant, and it could never be. The way the Kepler-Mann-Cohen definitions work, I mean, they cannot possibly give an exact constant of it by design. That precise. And the landscape, on the other hand, I mean, it's easy to compute. It's a computation invariant problem. To do it explicitly, it gives you the correct on spot. So the precision is that good. It actually gives you the correct threshold on the spot, and that's the difference with many generations of data spots. So sort of I mean the pictures that you have seen, because in principle, I keep saying that the landscape law has dimensional constants behind them, and that to me dimensional is like amazing because there is no dependence on potential, energy, and anything. The physics that apply dimensional can still be invariant. But the point is that factually the constant is gone for all practical purposes. And this is one example of application that is all. Just a few words about the proof this is really very, very different from the standard Bible considerations. But this is just to give you an idea of how much work. So in one direction, you are using this uncertainty principle business, and you are using concurrent hypothesis. So there are two directions, right? You need to bound the energy from above and below. So what's important? Uncertainty principle is important because it gives you the lower bound. So one of the bounds given by the uncertainty. It's not, as easy as it looks in the sense that uncertainty principle is global and what you are doing is local. So there is a certain, there are a lot of transitions that technologies define it, but with concurrent house. Long story short, uncertainty principle is one of the ingredients. But the interesting thing is that another ingredient is sort of really the one which makes you understand to a certain extent why Q is equal to 1 and not to 55, for example. Oh, 55 would be okay because you just divide by it, but know some other functions, something like that, is because this gives you the correct scale of variation. And that's basically the deal with the landscape, that it adjusts itself locally to this vision of the wave, because it adjusts itself locally to the correct variation. It's sort of not only if there are many things which can give you exponential decay wave. This tells you nothing inside, right? It's sort of pointed out, I mean, the only theorem I showed you so far pointed out that, well, the geometric one again, pointed out that you have an eigenfunction in a well, and then you control exponential decay wave. What I'm saying here is completely different. Not only I can do that, but it controls the shape inside. That's a completely complementary information. Because exponential decays away and the shape of the eigenfunctions inside. So using the landscape, you have a pretty good answers for the eigenfunction itself. Not only for how it decays, but also for how it swaps, for the main part. And the reason for that is that somehow the scaling, and you see it, for instance, like Mozart if you use it properly, because of the solution elliptic problem, you know how it oscillates, morally speaking. Like Mozart qualities, something like this. And don't know that it oscillates exactly correctly. It's going to oscillate on the scale by your eigenfunction can be. So it basically gives you locally an movement of the correct shape to host an eigenfunction at that place. So there is this simultaneous adjustment of completely complementary mechanisms. And the third mechanism is that the depth of the spell gives you an eigenvalue. So somehow what happens locally gives you the shape of the eigenfunction, the depth gives you the level of the eigenvalue, and the decay from is also bound by the landscape. And all of this is in one object. So some more information in physics, but in the remaining 5 minutes or so, let me talk about something that we don't know how to do, mathematically speaking, and which is really interesting and a next level of localization. It's the Wigner-Weil formalism. So once you figured out spatial and energy information, you become greedy and you want phase-space. And I am going to define Wigner functions. That's probably those that Simon decided not to define. So I will do that. And well, just as I was alluding to, the Wigner function is what gives you the portrait of the eigenfunction in phase space, not just in physical space, but in physical space cross phase space. Specifically, this is something that you can see defined above. I mean, it's a formula. Gives you the probability, the projection on x gives you the probability density on x, psi of x squared for an eigenfunction. And the projection on the momentum gives you the density of the momentum. So at some point simultaneously has the information about the momentum and the physical space in one object. On top of it, it's almost like a probability distribution for your eigenfunction and phase space. And what I mean by this is it's not super negative, meaning that it can be negative, but very little. It's sort of combined with the both with correct Gaussian, it's actually positive. This helps with some problems, not so for others, but morally, physicists will think about it as being positive. I wouldn't so much, but let's not argue on that. And secondly, the scalar product is preserved, and what it means is they are orthogonal to each other. And if you have a positive covariant, which is orthogonal, in this basis, it means that you have a competition. It means that they basically pave the phase space. So it's something born by your eigenfunction, which gives you a pavement of the phase space. And the good news is because of that, it gives you quantum observables. So I am using the bracket notation. Somebody was trying to avoid today, and so I actually use both here. So any quantum observable, so the value of the A in function C can be written literally as an integral of the function against the Weil sequence. So you have prediction for any operator. I'm saying that this is extremely powerful information because it's not only about energies, it's not only about space. It gives you predictions of operators, it gives you predictions of quantum observables. And Wigner function and Weil transform are basically just formulas, so you can do that. So what can you say about the Wigner function? Well, I'm going to try to give in 2 lines a very quick intuition. You read using the formula I just showed you before, you see that it becomes an integral of E against the layer like this. So it's basically an integral of the Wigner function on, well, give or take on the curve k squared plus 3 equals P. Slide a second. And it should be, morally, it's actually equal identically E against the diagonal, so against density of states. This is your probability when you read it, if you all done it. And already because one goes, this and this cannot possibly be the same. But already because we will prove the landscape over can conjecture that if you just blindly substitute 1/u, life is going to be a lot of, again, a big leap of faith. But turns out to be true computation. So you try to do this potentials. This is the example, and you just saw that we are sure we are not asymptotic again. There are some low energy, high energy functions, and not cheating. I know what low and high means. I mean, it's sort of completely different regimes, localized and delocalized. And in color here, you have a Wigner function, blue and red. And in black, you see the lines of k squared plus 1/u. The point of the picture is that basically the entire function is more speaking contained in the k squared plus 1/u. So yet again, you know the statement of the phase space again from the same landscape, both for low energy, high energy. Just to tell you that no, you're not going to be able to do it classically. This is the picture. So VF is 1/u. Some people call it effective potential, so depending on who did the computation. But V is the original potential. So you can see that if you try to play this game with the level 1 of the original potential, you avail. 1/u really gives you, sort of the support of the Wigner function, and moreover, it gives you the support in the bulk, but the actual curve of 1/u plus k gives you this region of positivity, which is another huge piece of information. So it's this escalates to 0. So if you take an integral, consider the inside, it's going to be 0. It again goes up and down, but it's almost never positive. Positive part is important, and that lies basically on k squared. It's 1/u plus k. This is not proved. I don't know how to prove any of this. We start discussing Regenia in particular. I can tell you that not only it's not proved, there is nothing to draw from. There is no semi-classical envelope. The only results on the Wigner function of the type that looking at are due to Hanin and Zaldich, and they do 2 cases. Well, there is one paper which does x squared, which does just the harmonic oscillator explicitly. For x squared, you can just write your eigenfunction explicitly, and they go to great detail of results. It's great paper, but I mean, for the particular results like this, it's this subset is almost trivial because the eigenfunctions are symmetrical, in phase and space. Because if they create a form of Schrödinger with harmonic oscillator, you get the same operator. So it's sort of symmetry. It's very algebraic, and it's explicitly looking at polynomials. And there is another paper by the generalized result just a few months ago, but it's potential which proves that affinity is x squared, which is smooth like x0 like x squared, which has convex level lines p. So like in short, it smells like x squared, it barks like x squared, like it looks like x squared. It's really not, anything beyond that. And it's not even possible to reformulate this somehow. I mean, like, first of all, as I already mentioned, I want like h goes to 0, but more importantly, in this case, it's possible to formulate that meaningfully if you want to prove some because somehow the taking h to 0 correctly sort of distorts the picture. Since you are working with x and c both on this boundary potentials, I mean, you cannot move it up correctly. Again, it takes a bit to explain, but well, you have to do it also from scratch, and I don't know how right now. Again, on this, but I think it's a very interesting. So with that, let me only mention that one example application of this is with the spectral functions. So this is the results which the experiments in particular for which Alon got his Nobel Prize. So this is the experiments of Alon Spec. And this is the experimental setup which got him the Nobel Prize. So you can remember the spectral function and system of cold atoms. Spectral function is basically, you push in a plane wave and you see the response of your system. There is a symmetrical formula which is not on this slide. But the point is, in red is state of the art. In green is, so in red is measurements experimental. In green is the semi-classical approximation. And in blue is the last. The ones which come from the spectral function results. So if you are in super high potential regime, you are really in the classical regime that's going to coincide with approximation, so it's sometimes still. So there is a way to make some classical approximation here, but again, if you go to the deep quantum, you see the difference. None of this is proved, and I hope we do one day. I will finish here actually. Thank you very much.
Thanks for the nice talk. Question?
So I have a somewhat late question. So suppose you have just a bounded domain, your potential is zero, so we can just reduce Laplace. And I would like to apply the Slutsky law. So do you think it would be feasible to get some bounds of this term that you can express in terms of the function, in terms of the geometry?
Yes, so on the spot of it, yes. So what you do is you compute solution to Laplace uniforms one with irregular boundary conditions, it's meaningful to exist, and then you do this counting. Right? You count the minimum. So the answer is
okay for some simple domains, like I don't know, it's this. Then you
exact, and I mean for I can do it for a square in my head, but you can sort of. So yes, for simple domains it's exact, but for
still have to count like it's probably exact.
But
yeah,
simple, right?
Usually boundary conditions are not morally different from having the potential extremely large outside, and then everything applies.
yeah, but
And it doesn't have to be very large.
Yeah, improving the sense that you are dreaming about, the domains that you are dreaming about, I don't know, because I don't know what you are dreaming about. So in short, the result would be true. This dimensional constants from above and below, it definitely would give, the correct count and lambdas, because it's just a multiplicative dimensional constant. But whether it would be, for the square, no answer, right? So whether it's improving something, you're probably not thinking about the square. And the answer is yes.
Okay, I'll tell you.
You see what I mean? Yeah. Mechanism, yes, but whether it gives a actual improvement depends on what.
Other questions?
So if your potential is single, for example, in LP space, so do we have this kind of landscape phenomenon or?
Yeah, it doesn't. So actually, all this alarm business, the one I'm showing you right now. Revive this. These are so the ones which are here, this is the optical speckle, and what it means is basically you think of it as take Gaussian potential and then basically square it. Okay. Something like this. So it's like heavily near zero, it's singular in many places and everything.
So like now for LP space, so it's possible for P larger than NO2.
Formally, yes, whether it proves no result depends. So I mean, the game is that all this stuff. And now the question is, again, you are comparing something that you know and you want.
Yeah.
And then don't know what you know and if you want, and then will take a patient. Because for us, I mean, just because you can't apply it, you sort of end up doing this instead. But I can tell you that this potential is kind of doesn't look like it, but it's really, very adoption.
So when you use the landscape function to compute the while law, do you know of the error term? Because the fact that it is a better approximation than the original while law seems to indicate the error term way different from what you know?
Well, so again, it's not asymptotic. I don't know if it improves the asymptotic, but on the surface of it not, because it has multiplicative constants from above and below. So it doesn't, even on the first order term, it can't have an error. I mean, it's not, the strength of it is that it's not an asymptotic result, but the price for it is that it comes with dimensional multiplicative constants. Whether, you can sort of pretend, because as I said, the actual proof, the actual set necessarily has dimensional multiplicative constants. The way we apply it has constant one. Whether there is, sort of a particular example, class of examples in which you can actually prove constant one result in the limit, I don't know, because all I try to do is avoid taking a limit ever. So I'm refusing to think about it, but maybe.
Questions? No? So let's thank the speaker again.